So you people can see my screen. I think it's visible. If it's not visible, then you can just interrupt me. Okay. Yeah. So someone is asking about to clarify assignments. So at this point, I mean, we are told not to discuss this year's assignment. So we'll be discussing some other questions which are related to the assignment, but not exactly the assignment questions. Okay. So I'm Lalit, and I'll be discussing a few questions based on weekly lectures. Yeah, we'll start then. Okay. Okay. Yeah. So the first question for today is we are given a camera with focal length 10, where all the rays pass through its camera center. That means the kind of projection that we have is perspective projection. So this implies perspective projection. So the principal point is located at 0, comma 0 in the coordinate system of the image plane, and the image plane is parallel to xy plane of the camera centric world coordinate system, and its coordinate axes are parallel to x and y axis respectively. So what does this mean? So we have a world coordinate system like this. So this is our world coordinate system which has x, y and z directions, and then somewhere at the front we have our image plane. Okay. So the image plane is such that uh, the principal point is located at 0, comma 0 in the coordinate system of the image plane. So that means this intersection of, oh, what is this by the way, z axis in the canonical form that was discussed in the lectures. Yeah, what is this z here? Can anyone tell me? Okay, so this is the principal axis, right? And the point at which this principal axis intersects the image plane, this is the image plane. So if we have this point of intersection here, this point is the principal point. Okay, and it's also given that the image plane is parallel to the xy plane. That means it's in the canonical way, and the coordinates, the xy axis of the images and the 3D space are parallel, which means that the image also has x-axis in this direction and y-axis in this direction. Okay. What is the focal length here? Can anyone tell me? Okay. What is the focal length? Can anyone just tell me that in this figure? What does it mean? I mean, I want this to be interactive instead of just me solving the answers. So just need some answers. If you don't know, it's fine. But I think Here we are just discussing the basics so that we can solve this question. Focal length. Okay, this is the focal length, right? This distance is the focal length f. Does anyone have any doubt on this? That this is the
No,
focal length?
yes, sir, no, sir.
It's clear, right?
Yes, sir.
Okay, okay, yeah.
Yes, sir.
So, so this is the focal length. So now, given that we understood the physics of the problem, we'll try to solve this problem. Okay. So what do we know about cameras till now? So there is a projection matrix P. P is the projection matrix. Okay. Which is given as what? K R I minus C tilde, right? What is the dimension of K? And what is K? K is the intrinsic matrix. What is its dimension? Yeah, someone was trying to speak. Yeah, you can just unmute yourself and say directly. It's fine. So its dimension
Three
is
cross
3 cross 3. Yeah. And what is R? R is what? R is rotation matrix, right? 3D rotation matrix. Its size is also 3 cross 3. And what is this matrix out here? This matrix which I'm underlining. What is the size of this matrix? This is 3 cross 4, right? Okay. I'm having difficulty in communicating, I guess. There's no responses out there. What is C tilde? C tilde, what is C tilde? What does it mean? It is a camera center. So instead of O, I should write here as C tilde. Okay. I hope this part is clear. Um, what are the different components of a projection matrix? So we first convert this question into maths form. What is K? So in the class, it was discussed that K is uh, given as F S Px 0 F Py and 0, 0, 1, where F is what? F is the focal length, but this is in units of space. For instance, millimeter or centimeter or other similar units. But what we generally want, we want to map 3D space to the 2D image, right? And in image, how do you measure any location? Location is measured in what? Pixels, right? So instead of F, this was discussed in class. Alpha x is f times uh, the number of sensors in the x direction. This is number of sensors or number of pixels. Both are same in this case. Number of pixels or sensors in x direction. F is the x direction per unit length. This is the focal length in unit length. So what does this alpha x unit look like? What would be the units of alpha x? It will be in pixels, right? Okay, not getting any response. So similarly, alpha y will also be f times ny. So with this, we get calibration matrix alpha x into s into px 0 alpha y py 001. Okay. So now we just read out the question. The principal point is located at 0 comma 0, which means what? Px is 0, py is 0. This is the principal point part. Okay. And what does this s mean? I should write it here. The s is tan of theta, where theta is the angle between the axis. Angle between the x and y axis in the image. So sometimes it's the case that the x and y axis are not exactly at 90 degrees, which means x could be like this and y could be like this. So they are not orthogonal. So in this case, we take theta. Sorry, here in this case, the theta should be the other one given the notation. Okay, so this is the theta. So for our question, there is no involvement of theta. So we take theta as 0. This is also given to us. Next is the focal length f. So here the focal length is given in pixels, which means that we are given alpha x equals to alpha y equals to 10. This implies s equals to tan of 0, which is 0. Okay. So our calibration matrix is set with these parameters. Next, we now look for the other matrices. Rotation r. How much is the rotation given? There is no rotation out here. So camera is aligned to the world coordinate system. So for this case, r is I. And next, if we check for c tilde, which is the camera center. Um, okay. So the camera center is also assumed to be at the origin, which means it's a zero vector. So given this, our projection matrix looks like what? We'll just replace the different components that we reduce now. Okay, so I just directly write 10 0 0 10 0 0 0 1. So this part is the matrix K, and the next part is R. R is identity, so I'm not writing it here. And then I'll write identity matrix here, and this is the C tilde part. So this is the identity. Here is the negative of C tilde, which is also the same. So given these, what do we need to find? We are given world coordinate 60, 90, 30. That means what are we given? X tilde is 60, 90, 30, which is given in which form is this? Non-homogeneous form. So with this, our homogeneous form will look like this: 16, 90, 31, which is given as homogeneous form. So I hope you recognize that these entities lie in P3, three-dimensional projective space. Okay, so given this, we just need to find x equals to px with the projection matrix that we found. 10, 0, 0, 0, 0, 1. And the given point in homogeneous form is 60, 90, 31. So what does this lead to? It gives us 600, 930. But since we know that this is a projection operation and all the points are similar, I mean all scale points are similar, so we can just scale it with the third dimension, which gives us 20 to 31. So the x tilde, which is the non-homogeneous form, that is the place at the pixel location at which the image will be formed, is 20 comma 30. Okay, is this clear? Any doubts on this question? Okay, I guess there are no doubts. It's too silent out here. Okay, so we'll do another related question to this projection matrix. So our next question is, if the principal point is located at 1 comma 2, which means our px is 1, py is 2, what would be the image coordinates of the world point? The given x tilde is in 6 7, it's given as 6 7 8. So we can write the equivalent homogeneous form as 6781, and focal length again is given as 2. So we consider focal length is given in pixels. 2 pixels. So how does the projection matrix look like now? So we'll just replace the values that we checked earlier: k r I minus c tilde, which gives us, for k we are replacing alpha x alpha y by 2, and px with 1, py with 2. Again, there is no rotation, so it's an identity matrix. Here again, it's an identity matrix, and the camera center is also at the world coordinate origin. So that's all there is to it. So given that we have p, we need to find what? P into x, which gives us small x, 6781. This leads us to um, answer like 22, 20, 22, 8. Okay. So if you now try to just make it into pixel coordinates, it will be 2.5, 2.75, and 1. So the point 678, which is in the 3D coordinate space, will be mapped to 2.5 and 2.75 on the image plane. Is this question fine? Any doubts in this question?
No doubts.
Okay, great. Okay, yeah. We'll move on to the next one.
Sir,
Yes.
camera center always to be taken as origin 000.
Not always, but in these specific questions, they are not mentioned as camera center. I mean, not specifically mentioned anything about camera center, so we are taking it as 000.
Okay.
So it's in the it's similar to the canonical setup that we do, where R is identity and C is 0. Okay, yeah. The next question, we need to compute the vanishing point in the image plane R2 of a line with direction ratios 1, 2, 3 in the given projection matrix. This. So you are given three direction ratios. What does it mean? Line is lying in which space?
P3.
Yeah, it's in P3. Yeah, correct. So, so when we generally write it like this, okay, it means that the A is 1, B is 2, and C is 3. So this is a line in P3. Okay. So how do so given two parallel lines in P3, where do they meet?
At vanishing point,
Vanishing point.
No, no, no. I'm talking about in P3 now. I'm not talking about image plane.
Vanishing line.
Sorry?
Vanishing line.
No, no, no. Vanishing lines and vanishing points lie on image planes. I am saying that if you are given two parallel lines in 3D space, rather P3, where will they meet?
focal point,
No, no. Okay, so if you are given two parallel lines in P2, like we saw it in the last week, not this week, where do they meet? Okay, how does it look in 2D? Ax plus by plus c equals to 0, or rather c1 equals to 0, ax plus by plus c2 equals to 0. If we write it in uh, homogeneous coordinates abc1, this will turn out to be abc2. So we need a point x such that it's 0, right? Okay. Okay, yeah, we'll discard this part for now. Sorry about that. Okay, so what I was trying to say is if there are two parallel lines in 3D, like two parallel lines in 2D meet at the line at infinity, right? Similarly, two parallel lines in 3D meet at plane at infinity. So if you see here for the 3D case, if I give ABC D1 and ABC D2, and these both should satisfy. Sorry. Yeah, these both should satisfy what? X, Y, Z, W. This is a point in P3. This both should satisfy these two lines. If there exists a point which lies on the two lines, which means that
Cross product is 0.
here you can't take cross products. Okay, yeah. Okay, I'll clarify this specific thing in the next session. So we'll just proceed with the question for now. Okay, yeah. So we are given P as minus 3, 2, 1, 6, 5, 2, minus 6. And we are given the direction ratio 1, 2, 3. That means the direction ratio is given as 1, 2, 3, and the point of intersection of these parallel lines is given as what? D comma 0, right? This is the point of intersection of parallel lines in what? Parallel lines with D as the uh, direction vector. Okay, so since all of these yeah, so that line of infinity or plane of infinity, what I'm trying to say, since any sorry about this. So any point in P3, if it's in this form where this is a 3 cross 1 vector and there's the last element is 0, this means that all these points lie on a line L, or no, not a line, it's a plane actually. So can anyone guess what this plane will look like? Is this fine? So if you have plane at infinity defined like this 0, 0, 0, 1, that means all the these points at infinity lie on a plane whose normal vector is given by pi infinity. Is this part clear? So here we are in P3 space, 3D projector space, just to be clear. So similarly, if we look at the 2D space that we checked earlier, where D is a 2 cross 1, here we had line at infinity equals to 0, where the line at infinity was given by 0, 0, 1. So any point of this form will always satisfy this line, will always lie on this line 0, 0, 1. Okay, so coming back to the question, where are we? Yeah. So we were given the projection matrix and the direction vector D, which is 1, 2, 3 in the cosine ratios. So given this, how do we get the vanishing point V? P times D0. So we are trying to map the point at infinity to the image plane. So where it maps, we call that position as vanishing point. So if we write it explicitly, we get this answer. Is this question clear?
Yes.
Okay. Okay. Yeah. So again, we are given a projection matrix, given an image point 1, comma 2 in R2, compute its scene point. That means we need to compute the 3D point. If the camera is at a distance 10 units from the camera center. Okay. So what does it mean? We need to define that ray mathematically, whatever ray we have here. So for defining a ray, what do we need? We need a starting point and the direction vector. The starting point we know here is C tilde, which is the camera center. And this direction vector, we can get it from the projection. Okay, how do we get it? So we'll first try to compute the starting point. How do we get the starting point? We know that PC equals to 0, where C is the camera center in homogeneous coordinates. Since C is a singular point, so our P into C should be 0. So if we try to break down this camera matrix as M into P4, and this is C tilde 1, we get from here C tilde is minus M inverse P4. Is this part clear? Or just I'll write the step here. M C tilde plus P4 equals 0, which leads us to this equation. So given, the camera matrix, we can always compute the camera center. So this is known now. And the next thing is we need to get the direction through which our ray should go. And we are given the units, distance. We are already given the distance in units. So if we get the direction, we can move further. So how do we get the direction? We know that x is given like this. Since we want to get the direction, this will be represented by point at infinity, which is in P3 space. Okay. So what is the x that we are given? X is given as 1 2, but it is given in homogeneous coordinate system. So with this, okay, I'll not write the explicit forms for now. So we can see that md equals to x, d equals to m inverse x. So with this two quantities that we know, we can define a ray like what? We start from the camera center, right? This is the camera center, and then we move along the direction with the scale mu, and the direction is specified by d comma 0, where d is again m inverse x. So given these quantities, what can be done? We will try to take common parts, mu x y minus p4, yeah, mu x minus p4, and this will be 1. The last coordinate will be 1 because here it's 0. Okay. So now we are given the matrix P. So from where we can get M? It will be quite straightforward. We just take the first 3 columns of the matrix P and we compute M inverse, which leads us to something like this. Okay, so this is given. We are given mu as 10. Yeah, we are given mu as 10. X is 1 2 1 because it's in homogeneous coordinate system, and we know the p4 from the matrix itself, which is 0 0 1. From this we can compute x at 10, which turns out to be something like this. Is this question clear? Any doubts in this question?
No, sir.
Okay. Okay, so yeah, we are given another projection matrix and the camera center is given as O. From the projection matrix, what can we tell about the camera center? Just seeing the projection matrix.
Camera center is at origin.
Yeah, that's right. Camera center is at origin. So we are given two image points. X1 as 2 3 1. I'm writing it in homogeneous form. X2 as 7 5 1. Find the unit normal to the plane OX1 X2. Okay. So the image will look something like this. This is O. This is X1. This is X2. If I try, so this is the plane that we are talking about, and we need to find the normal of the plane, which will look something like this n. Okay, so unit vector, so I'll put a hat. So first what we'll try to do is try to find the line, and finding a line is easy in this space, which is just x1 cross x2. If I write it like this, ijk 231751. This leads us to minus 25 minus 11. Okay, so this line is in which space? In the image space, right? It's on the image plane. So we know that this line, I will write it as, okay, this line L prime transpose x should be 0, where x is in the homogeneous coordinates. But we obtained x from the projective matrix Px, projection matrix Px. So we can just write it simply as L transpose Px be 0, or equivalently x transpose, I'll write it like this, L transpose P x equals to 0, or P transpose L whole transpose x equals to 0. So this gives us what? This x is in P3, 3D projective space. So this line is a 3D line. So what we ultimately need to find is P transpose L prime. So we are given P like this. Okay, we need to take a transpose here. P transpose L prime. What was our L prime? Minus 2 5 minus 11. So which leads us to minus 6 minus 24 minus 10 and 0. If you multiply this matrix and vector. So the unit direction is what we need, and that is, we'll just consider the first 3 elements for the unit direction. So it will just be 1 by square root of minus 6 square plus 24 square plus minus 10 square times minus 6 minus 24 minus 10. Is this one clear? How to find a plane normal given 2 points and the camera center? This question is fine, right?
Yes, sir.
Okay. Yeah. So we are given the left and upper matrix, two cross three upper matrix, which is given by M two cross three of a three cross four projection matrix P. Okay, so our P looks something like this: M11, M12, M13, M21, M22, M23, M31, 32. Okay, so this is the matrix M that we have seen in the class lectures, and this is the P4, the fourth column of the matrix P. Okay, so given the left upper triangular matrix 2 cross 3, so you are just given this part, given 2 rows and 3 columns, which means you are just given this part. This is denoted as M2 cross 3 of a 3 cross 4 projection matrix. Okay, which of the following satisfies for computing the direction of parallel projection D? Okay, can anyone answer this? What is parallel projection? Parallel projection is obtained from which kind of camera? There is a specific kind of camera that was discussed in the lectures. Okay, so it's given by affine camera. So in affine camera, if you remember properly, so this is a given scene point, and this is the direction in which the parallel projection should happen. So this one only projects in this direction. So there is no center of projection here. So everything is projected in a parallel sense. So all these are in direction D. So these are two distinct points and they map to two distinct points on the image plane. Okay, so for affine camera, is there any special form of the matrix that we know?
M31, M32, M33 are 0 and P4 3 is 1.
Yeah, correct. So with affine camera, we know that the last row, the first three elements of the last row are 0 and P4 3 is 1. Okay, so we are given a direction D. So with affine camera, if you are projecting along the direction D, this property holds. P into D0 should be 0. So if we just write out the matrix like this, so here it's P41, P42, and it's 1, D0 is 0. This leads us to M2 cross 3 into D. This is 3 cross 1 by the way. Yeah, is 0. So the correct answer is C. Is this fine?
Yes, sir.
This only holds for affine camera when projecting along direction D. Okay. Why does this hold in affine camera? Can anyone say that? What does this D comma 0 imply in affine camera? Why did I say that it's equals to 0 directly? Should be some meaning to it, right?
We can multiply using the last row so that it will become zero. Like matrix multiplication will be zero.
No, 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 no. So what I'm saying is this D0 is a singular point of the matrix P.
Because all lines are parallel.
No. Okay. But it's not necessarily the case, right? For a general projection matrix. What is so special about affine camera? This is the camera center of affine camera. Which means what? What does this even mean?
Camera center will have only two axes.
No, no, no. This is 3 cross 1. This is 3 cross
But the
1.
last row is zero. So it should be only two.
No. Um, I mean, I want to know the physical meaning of it. It's okay. The last row here is 0 and this is 1. That's fine.
Camera is at infinity.
Yeah, camera center is at infinity. Is at infinity. When is this possible? That the camera center is at infinity? There was one condition under which the camera centers will go to infinity, right? So if you see this matrix M, it should be singular. When M is singular, implies camera center is at infinity. This is always true. What is so special about the affine camera? That the last row is full of zeros. So if it's full of zeros, it's by default singular, right? It is not invertible. When it's not invertible, that means the camera center is at infinity. So for affine camera, our camera center is always at infinity, which is in again P3 space, three-dimensional projective space. Is this fine?
Sir, like how does that like mean? Like if camera center is at infinity means how does it like, physically, sir?
Okay, I'll give you an intuitive example. So what we have
Yes.
seen in the projective case, projective perspective projection. So we see that there is a center of projection through which uh, all the rays come here like this, right? So any point lying on this ray will map on to the images at these specific points, right? Is this clear?
Yes, sir.
But if I keep the image plane fixed here and move this very far away, it's like far away to
Okay, sir.
infinity. Then how does it look like? If I move this far away, then all the lines will almost be parallel here, right? It is something similar like the sun rays coming to Earth. We consider them as parallel because
Oh, yes, sir.
it's so far away that we just seem that everything is in straight line. But of course, they are coming out from a. I mean, you can assume if we assume that sun is like a point-sized object, then it's coming out in some angle. But since we are so far away that we can approximate it to be what as parallel lines.
Parallel.
So here again the
Okay.
same for the case of affine camera. So this camera center lies at infinity. So here it's a general perspective camera.
So if the camera center is very far from the object, then we can
Not from the
assume that like
object. Not from the object.
object
What is this? This is the image plane, right?
image plane.
Yeah. If it's far away from the image plane, then you can think of it like affine camera.
Okay. So like I'm very like getting confused between this object like image plane and all. Like, is there any other way like we can get more clear explanation?
Objects are these 3D points from where they are fixed. Objects are fixed.
Fixed. Okay.
So based on where your center of projection is, you just need to connect one line from the center of projection to the object, or rather the 3D point. And
Okay.
that line, wherever it intersects this image plane, you get the image point. That's all.
Oh. So image plane is like image sensor.
Yes, yes. For I mean, yeah, whatever we use now, it's the image sensor. Yeah, the CMOS sensor, it's generally used.
Okay. Okay.
The CCD sensor, which was discussed in the class, which we also checked
Okay.
at few, I guess, in the first question, at how to convert a focal length in millimeters to focal length in pixels. Right?
Yes.
Yeah, the similar thing. Okay.
Okay. So do you have any other resources where like we can go with the parallel to get more understanding of the concepts?
You
Because
can try
for the
reading the
seeing
book.
this,
You can try
yeah,
reading the
are there
reference
any
book.
other online resources like video something like any YouTube
For
channels?
online resources, I'm not aware that for this specific topic there are any better videos. But yeah, you
Okay.
can always refer to that book, Hartley and Zisserman, which is of course kind of extensive,
Yeah.
but that's foolproof. I mean, you if you read that, you will have clear concepts about it.
So, but
Okay.
that
So it
explains only theoretically. If we have to understand with the numericals, any
So numericals, I'm trying to do a few, but of course this is not sufficient. I understand that.
yes, sir, because 1 hour like course is only like it'll take around 2.5 hours, but you are covering only 1 hour, and so
Yeah, I mean, we can't do that for two
yeah,
and a
yeah.
half to
So
three hours.
we can understand that slowly.
Yeah, but that's true. I mean, the only thing I can say is just try solving assignment questions.
Okay.
Hopefully this is helping some of the assignment questions, not all of them.
Yeah, yeah. This like this video like 1 hour session is like literally helping a lot because we are able to clear our doubts easily.
Okay, okay.
Yeah, but the thing is we are completely beginners, so like for seeing the videos only for one time is not like we are not able to understand. So that's why I asked for
Okay, okay, okay.
other resources.
So maybe you can just do it this way. See the videos,
Oh,
and then for that
yes, sir.
specific topic, just look in the book if you don't find it clear enough.
Okay. Is
If
the
you
book beginner friendly? Because some books are like even
I mean,
they.
they look daunting, but they're not that. I mean, hard. Most of these
Okay.
things are simple linear algebra based. You're just seeing that we are just playing with lines and points.
Yeah, yeah.
So it looks daunting, but once you understand what it means physically, you can easily try to correlate it.
Correct. Yeah, exactly.
Okay, so
And like if we want any like about like computer vision using practically, so will the course like in the future episodes will that provide or should we need to look into external resources?
practical means in what sense?
Like any real life application, something like that. Because here
Okay.
we are just going with more of theoretical, right?
Okay, so you need this theory. Whatever was done this week, last week,
Okay.
you need this theory. A few
Okay.
of these examples were given, if I remember correctly. One is the homography example, right?
Yeah.
So
Yeah.
when
Yeah.
you take your camera and then, I mean, mobile phone camera, and then you try to take a panorama of the area of the
Yeah.
scene around you. So that's nothing, just a homography. You're trying to correct the different images using homography, and then we get a stitched image, right?
Stitched image. Okay.
So all these things
Yes.
are, I mean, these are practical, but if you don't know this, you cannot implement it.
Implement.
Well,
Yeah.
I understand that you might be interested more in coding aspect than doing this,
Yeah. Exactly.
but for that, there are, I mean, you can just directly try to code these things, and there are implementations available as well.
Okay.
If you use OpenCV, if you ever used OpenCV in Python, or it's even available in C++, you can try that.
Okay. Okay. I'll look into it.
So there it's quite, I mean, OpenCV is considered one of the best libraries you can use, and it's easy to
Yeah.
use for the basic
Yeah. So
basic
they would have already implemented all this math stuff for there. Like they'll give it as a function, so we can directly use it.
Yes, 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 yes. Of course,
Okay.
given the current set of lectures, you won't be able to understand that fully. I mean, I guess you
Yeah.
need a few more weeks to understand that what they do exactly in their implementations.
Their implementation. Yeah.
See,
So if we are
because
able to
yeah,
get their implementation, then we can say that okay, we are good at computer vision, because using OpenCV also doesn't mean that we completely know about computer vision, right?
yes, that's true. At least for the
Yeah.
basics, yeah, you should focus on the basics because now
Basics.
no one
Yeah.
can know any topic completely.
Yeah. Yeah.
That's it. Okay, so we'll just do one more question, I guess, before
Okay.
we disperse. But by the way, yeah, someone asked about this year's assignment question, but we are told that we should not solve this year's assignment question strictly. So that's the reason I'm avoiding it. But most of the questions are similar, if I know correctly. I have not checked this year's assignment questions. Okay, so we are dealing with projection matrices completely. Of course, the lectures were on projection matrix. So we are given a projection matrix and we are given points like this. Okay. So this is our image plane. So we have x2 comma 5 somewhere. Just write x1 somewhere here. X2 is 7 comma 9. X3 should be somewhere here. X is and x4 should somewhere be here. So just to let you know that the whole thing is on the plane, and this is the 3D coordinate space. The red one is the image plane that we are looking at. So compute the dihedral angle between the planes OX1, X2. We have planes O, then X1 and X2. So this is similar to one of the questions that we did earlier. And X3, X4 is another line, and this is another plane. So dihedral angle means what? So we have normal from these two points, I mean plane to this normal, and we have normal from these 2 points. Okay. Okay. So again, in a similar way, for we first try to find the line containing the points x1 and x2, which is just x1 cross x2, which gives us -4, 5, -17. These are just simple computations. And the line 3, 4, which contains the points x3 and x4. 4, 5, -11. Okay. So given these two lines, you now need to form planes. How do you form planes? We just checked it right now in the last question, I guess. So this is line in image space, right? And this is the line. Oh, sorry. Yeah. This is a plane in the 3D space or P3 space. This is P2 space. Plane in P3. So we just try to compute these two. No, I mean simple multiplications. There is nothing complicated. transpose L34 will give us something like this. How do we compute angles between? Okay, so these are what? These are the plane parameters. This is pi 1 2, this is pi 3 4. So it should be like x tilde 1 equals to 0. Any point satisfying this plane will be of this form, any point satisfying this plane will be of this form. So we are only interested in the normal part, which is what? Just the norm of, I mean, 1 by norm of this vector. That's 14105 minus 107. If we take norm of this, and similarly for N34, so it's just a Euclidean norm that you generally take. 56, okay. So given these two normal vectors, how do we compute the angles between two vectors? So in general, we know this thing, right? Cos theta is, if you are given, I'll write it as a different way. So this is the angle between two vectors in any space, any real, any real space. So here we need to find the angle between pi 1 and pi 2. So it will just be n1 hat 2 transpose n134 hat upon norm of this, which is 1, since we already normalized it. And with this we'll try to take the cos inverse. So our theta will come in which units if you do it this way?
Radians.
Yeah, it will be in radians. Yeah. So in exam, if you're asked about degrees, then you have to convert the radians into degrees by multiplying 180 by pi. Okay. Okay. So yeah, with this, I'll stop today's lecture.
Hello,
Yes.
sir. Can we get your LinkedIn if you have?
Sorry.
Do you have LinkedIn?
You can just search my name. I mean, it's not that
I
difficult.
searched. I didn't get so only.
Okay. Okay. Fine. Yeah, you can just. Can you see my email ID here? It's not.
No.
Okay, you can just. What's your name? Lakshman, right?
Lakshman. Yes.
Okay, fine. Okay, let me stop recording first.
Yeah. Okay. Okay.